Okay, so we'd like to sort of get a handle on how we can look at this. And so in each row, there's a leading variable. So for example, first row, X is leading. Second row, I don't think that's legible. Second row, Y is leading. So in this form here, as well as this form here, it doesn't matter. It's the first non-zero coefficient. So even though there's a zero here, X is leading in the first row, Y is leading in the second row. It's the leftmost term that has a non-zero number in front of it. Okay. Now, it's an echelon form if the leading term, the leading variable in each row has nothing underneath it, right? So here, there's no X term under this wouldn't be an echelon form because the leading variable in the first row has a term under it, right? So this is not an echelon form. So to get it an echelon form, we want to get rid of this term here. And that was what I did with this first row operation, was to put it. So it's sort of like a staircase. Now, let me give you another example of echelon form so this makes sense. If I had X plus 2Y plus 3 Z equals 8 and 4Y plus 2Z equals 24 and 5Z equals 7. Well, this system is an echelon form. I've just written it down right away because the leading term in the first row is X. It has nothing underneath it. The leading term in the second row is Y, and it has nothing underneath it. And the leading term in the third row is Z, and it has nothing underneath it. So it's sort of like it has to make a staircase where each row has to be to the right, sort of has to start to the right of the row above it, right? So it doesn't have to be just one thing. It could, another echelon form could be X plus 2Y plus 3Z plus 4W equals 9, and then 5Z plus 6W equals 18. There's another linear system that's an echelon form. So X is leading, and Z is leading, and the leading variables have nothing underneath them. Okay? Now, it turns out that you can see here that there's for this system here, there's other variables that aren't leading. Like Y is not leading, and W is not leading. So variables that are not leading are said to be free. So that's the definition of free variables. They're ones that are not leading. So now the free variables and leading variables only applies in row echelon form. Like you could look up here and say, well, X is leading and X is leading here. That just means it's not an echelon form. If you want to identify which variables are actually leading, you want to go to echelon form and then say, okay, well, X is leading and Y is leading. It's an echelon form. X and Y are leading. All the variables are leading. Here, X is leading, Y is leading, Z is leading, all the variables are leading. But here, X is leading, Z is leading, but Y and W are free. So a system can have any number. It can have all the variables can be free, all the variables can be leading, some free. So there's just a way. Now, so let's go back and say, okay, we have this system here. Let me copy it down below. I think it is X plus 2Y equals 4 and Y equals 1. So the method we use to solve this equation is called back substitution. And it's back because if you notice, what we did here is we sort of proceeded the procedure. This is going to be true for all systems. You sort of proceed from the top row, you clear the first column, then you move to the right and clear the second column and keep moving sort of down and to the right. So you're sort of moving down you're sort of moving forward like that. And so back means, well, you're going to go back up this way. So what we do is you're going to start from the last equation, and it only is going to have one leading variable. So you're going to solve for that leading variable in terms of constants, or maybe other free variables. We'll see that in a second. So here we'd say, okay, well, we would say, well, we see y is equal to 1. So then we can use that to substitute for the leading variable in the previous equation and have x plus 2 times 1 equals 4. And then x equals 4 minus 2 equals 2. And you've solved the system. You found that this system only has the pair of solutions 2, 1. And this is called an ordered pair. And that's one way of recording the solutions is because if I write down the solution as 2, 1, I always mean the first slot is x and the second slot is y. This order, because this order is kept here, x, y, the order in an ordered pair is always the same as in a linear system. So there's no ambiguity. But we're not going to actually finally record. We're going to record these solutions in another way. We're going to write this solution like this. And we're sort of jumping the gun here a little bit, but we're going to say this is going to be a vector. We're going to call this a vector. But it's just like an ordered pair, but we're going to find out that vectors can do stuff. So and the only difference here is you have written it vertically, and I haven't written the comma. Okay. So this is a column vector because it's written in the column. So we're going to write our solutions in terms of column vectors. In fact, since some systems have an infinite number of solutions and some systems have no solution, we're always going to write our solutions as a set. Okay, a set is a collection. A set is a collection. So we're going to write the solution to this first system as a set. For example, here, the set A equals the numbers 1, 2, and 3 is we use curly braces. If I write them more clearly, they look sort of like this. We use curly braces to enclose the elements or members of a set. So here, we're going to write the solution to this first linear system as this, as a set of vectors. Okay, so let's see.